NENOMATICA, where mathematics meets YouTube excellence. Exponential equations. Let's solve the following exponential equations step by step, following the exact structure and logic shown. We start by dividing all terms by 25 to the power of x to get all terms with the same denominator. When we divide 25 to the power of x by itself, we get 1. Now we can rewrite these fractions in a different form. 4 equals 2 squared, and 9 equals 3 squared. So 4 over 25 is equal to 2 over 5 squared, and 9 over 25 equals 3 over 5 squared. With some experimenting, we might try a value of x equals 1/2. Let's see what happens when we substitute this value. When the exponent is 1, we just get the base. So we have 2/5 plus 3/5, which equals 1. This confirms that our solution is correct. The solution x equals 1/2 is the unique solution to this equation. This follows from the reminder. If the equation a to the x plus b to the x equals 1, where a and b are both between 0 and 1, has a solution, then this solution is unique. Let's examine this problem. We need to solve the equation where x minus 2 raised to the power of x squared minus x equals x minus 2 raised to the power of 12. To solve this exponential equation, we'll use the principle that when the bases are equal, the exponents must also be equal. However, we need to consider special cases as well. Let's explore both approaches. Let's start with case 1, where we set the exponents equal to each other. If the base x minus 2 is not 0, 1, or -1, then we can set the exponents equal. X squared minus x equals 12. Now we can rearrange this to standard form x squared minus x minus 12 equals 0. Now we can solve this quadratic equation. We get x equals -3 or x equals 4. For case 2, we need to check special values of the base x minus 2. When a base is 0, 1, or -1, we need to check each case individually because these bases have special properties with exponents. First, let's check when x minus 2 equals 1. This gives us x equals 3. Substituting back, we get 1 raised to the power of 6 equals 1 raised to the power of 12. This is true, since 1 raised to any power equals 1. So x equals 3 is a solution. Next, we check when x minus 2 equals -1. This gives us x equals 1. When we substitute, we get -1 raised to the 0 power equals -1 raised to the 12th power. Now, 0 as an exponent gives us 1, and -1 raised to the 12th power is also 1 because the exponent is even. So x equals 1 is also a solution. Finally, we check when x minus 2 equals 0. This gives us x equals 2. Substituting back, we get 0 raised to the power of 2 equals 0 raised to the power of 12. Since any power of 0 is 0 except 0 to the power of 0, both sides equal 0, and x equals 2 is also a solution. To summarize our findings, this equation has 5 solutions: -3, 1, 2, 3, and 4. The complete solution set is the set containing these 5 values. Let's double-check each solution by substituting back into the original equation. We'll find that all 5 values satisfy our equation. In conclusion, we solved this exponential equation by considering 2 cases: when we can equate the exponents directly and when we need to check special base values. This approach is useful for solving many types of exponential equations. Today we'll solve an exponential equation step by step. Let's start by observing that 2 minus square root of 3 and 2 plus square root of 3 are reciprocals of each other. This means that the first term can be rewritten as 1 over 2 plus square root of 3 to the power of x. Let's also substitute y equals 2 plus square root of 3 to the power of x to make our equation simpler. Using our substitution, we can rewrite the equation as 1 over y plus y equals 4. To eliminate the fraction, we'll multiply both sides by y. This gives us 1 plus y squared equals 4y. Let's rearrange to get the standard form of a quadratic equation. Y squared minus 4, y plus 1 equals 0. Now, we can solve this quadratic equation using the quadratic formula. The solutions are y equals 2 plus or minus square root of 3. Now, we need to find the values of x by substituting our y values back into our original substitution. For the first case, when y equals 2 minus square root of 3, we have 2 plus square root of 3 to the power of x equals 2 minus square root of 3. we can observe that 2 minus square root of 3 is the reciprocal of 2 plus square root of 3, which means 2 plus square root of 3 to the power of -1. Therefore, x equals -1. For the second case, when y equals 2 plus square root of 3, we have 2 plus square root of 3 to the power of x equals 2 plus square root of 3. This means x equals 1. Therefore, the solution to our exponential equation is x equals -1 or x equals 1. We've shown how to solve this exponential equation by using a clever substitution and noticing the relationship between the terms. This approach turned a complex exponential equation into a more manageable quadratic equation. Welcome to this math video. Today we're going to solve an exponential equation with absolute value. Let's start with our example problem. We need to solve the equation where the absolute value of x minus 3 raised to the power of a fraction equals 1. The exponent is x squared minus 4x plus 3 divided by x minus 2. When solving equations of the form f of x raised to the power of g of x equals 1, we need to consider two special cases. The first case is when f of x equals 1 and g of x can be any real number. The second case is when g of x equals 0 and f of x is greater than 0. Additionally, we need to be careful because if f of x is less than 0, we may still have solutions that require further validation. Let's tackle the first case where the absolute value of x minus 3 equals 1. Using the definition of absolute value, this means either x minus 3 equals 1 or x minus 3 equals -1. From these equations, we get two possible solutions, x equals 4 or x equals 2. Now, we need to check if these values are valid by substituting them back into our original equation. Let's examine x equals 2 first. For x equals 2, the denominator of our exponent becomes x minus 2, which equals 0. Since division by 0 is undefined, x equals 2 is not a valid solution. Let's examine the second case, where the exponent equals 0. We set the numerator of our fraction equal to 0 and solve the resulting quadratic equation. Factoring this, we get x squared minus 4x plus 3 equals 0, which gives us x equals 1 or x equals 3. We need to check these potential solutions as well. For x equals 3, the absolute value of x minus 3 becomes the absolute value of 0, which equals 0. At this point, we would have 0 raised to some power equal to 1, which is impossible since 0 raised to any power is 0, not 1. Therefore, x equals 3 is not a valid solution. Let's check x equals 1. For x equals 1, we have the absolute value of x minus 3, which is the absolute value of 1 minus 3, or the absolute value of -2, which equals 2. The exponent becomes x squared minus 4x plus 3 divided by x minus 2, which is 1 squared minus 4 times 1 plus 3, all divided by 1 minus 2. This simplifies to 0 divided by -1, which equals 0. So we have 2 raised to the power of 0, which equals 1. This matches our original equation. So x equals 1 is a valid solution. Let's check our final potential solution, x equals 4. For x equals 4, we have the absolute value of x minus 3, which is the absolute value of 4 minus 3, or the absolute value of 1, which equals 1. The exponent becomes x squared minus 4x plus 3 divided by x minus 2, which is 4 squared minus 4 times 4 plus 3, all divided by 4 minus 2. This simplifies to 16 minus 16 plus 3, which is 3 divided by 2, giving us 3 over 2, or 1.5. So we have 1 raised to the power of 1.5, which equals 1. This matches our original equation. So x equals 4 is also a valid solution. Therefore, our final answer is that the solution set consists of x equals 1 and x equals 4. We can write this as D equals the set containing 1 and 4. Let's summarize the key steps we used to solve this problem. First, we identified that for an equation of the form f of x raised to g of x equals 1, we need to consider two cases, either f of x equals 1 or g of x equals 0. Second, we solve for values that satisfy these conditions. Third, we carefully checked each potential solution by substituting back into the original equation. And finally, we found that x equals 1 and x equals 4 are the only valid solutions to our equation. In this video, we're going to solve an exponential equation. Let's examine the problem step by step. For equations of the form f of x raised to the power of g of x equals 1, we need to consider two special cases. Let's solve this equation by examining both cases. Case 1, when the base equals 1. In this case, x squared minus x minus 1 equals 1. This simplifies to x squared minus x minus 2 equals 0. Using the quadratic formula, we get x equals -1 or x equals 2. Now let's consider case 2, when the exponent equals 0. In this case, x minus 1 equals 0, which gives us x equals 1. Therefore, combining all our solutions, the final answer is D equals the set containing -1, 1, and 2. This completes our solution. We found three values x equals -1, x equals 1, and x equals 2 that satisfy the original exponential equation. Welcome to our mathematics tutorial. Today, we'll solve an exponential equation involving trigonometric functions. Let's look at our equation, the absolute value of cosine x, raised to the power of sine squared, x minus 3/2 sine x plus 1/2 equals 1. When solving an exponential equation in the form f of x raised to the g of x equals 1, we need to consider two specific cases. The special cases for this type of equation are, case 1, f of x equals 1, and g of x can be any real number. Case 2, g of x equals 0, and f of x must be greater than 0. We should also note that we might still have solutions when f of x is less than 0, but we need to carefully check validity. Now, let's apply this to our specific problem. In our equation, f of x is the absolute value of cosine x, and g of x is sine squared x minus 3/2 sine x plus 1/2. Let's start with case 1, where f of x equals 1. So, the absolute value of cosine x equals 1. We know that the absolute value of cosine x equals 1 when cosine x equals positive or -1. This happens when x equals k pi, where k is any integer. Now let's move to case 2, where g of x equals 0. So, sine squared x minus 3/2 sine x plus 1/2 equals 0. This is a quadratic equation in terms of sine x. Let's try to factor it or use the quadratic formula. Actually, we can rewrite this as sine x squared minus sine x over 2 plus 1/2 equals 0. Let's simplify. Sine x squared minus 3/2 sine x plus 1/2 equals 0. If we let u equal sine x, we get u squared minus 3/2 u plus 1/2 equals 0. We can solve this using the quadratic formula, but I can see from the original image that it directly shows the solutions. One solution is u equals 1, which means sine x equals 1. The other solution is u equals 1/2, which means sine x equals 1/2. When sine x equals 1, we get x equals pi over 2 plus 2k pi, where k is an integer. But we need to check if this is compatible with our requirement in case 2. When sine x equals 1, cosine x equals 0. But we need to avoid situations where cosine x equals 0, because that would make our original f of x value also 0, which doesn't work with case 2. So, the solution sine x equals 1 actually creates an invalid case. Now, let's find the values of x when sine x equals 1/2. We know sine of pi over 6 equals 1/2, and sine of 5 pi over 6 also equals 1/2 because of the symmetry of the sine function. Therefore, x equals pi over 6 plus 2k pi, or x equals 5 pi over 6 plus 2k pi, where k is any integer. Now, let's combine all our valid solutions. From case 1, we have x equals k pi. From case 2, we have x equals 2k pi plus pi over 6, and x equals 2k pi plus 5 pi over 6. Therefore, the complete solution set is D equals the set containing k pi, 2k pi plus pi over 6, and 2k pi plus 5 pi over 6, where k is any integer. To summarize, we've solved this complex trigonometric exponential equation by, first, identifying the special cases of the general form f of x to the g of x equals 1. Then, solving case 1, where the absolute value of cosine x equals 1. Next, solving case 2, where the exponent equals 0, which led to a quadratic equation in sine x. Finally, combining all valid solutions to get our complete answer. Welcome to this mathematics lesson. Today we're going to solve an exponential equation involving trigonometric functions. Let's start by rewriting cotangent in terms of tangent. We know that cotangent x is the reciprocal of tangent x. So we can rewrite the right side of the equation as 1 over tangent x to the power of cosine x. Now, let's rearrange the equation. We'll move all terms to the left side. When we move the right term to the left, it becomes tangent x to the power of cosine x, and the whole expression equals 1. We can simplify this expression by using the law of exponents. When multiplying expressions with the same base, we add the exponents. So we get tangent x to the power of sine x plus cosine x equals 1. For an equation of the form f of x to the power of g of x equals 1, there are two main cases to consider. Let's list them. Let's analyze the first case, when tangent x equals 1. This gives us x equals k times pi plus pi over 4, where k is any integer. For the second case, we set sine x plus cosine x equal to 0, and we also need to ensure that tangent x is positive. This gives us these ranges for x. Let's solve the equation sine x plus cosine x equals 0. First, we rearrange it to get sine x equals negative cosine x. Next, let's divide both sides by cosine x to get tangent x, assuming cosine x is not 0. We get sine x over cosine x equals negative cosine x over cosine x. This gives us tangent x equals negative 1. Solving for x, we get x equals k times pi minus pi over 4. Now, we need to check which solutions satisfy our constraints. After checking the conditions and constraints, we find that the final solution set D is the set of all values of x of the form k pi plus pi over 4, where k is any integer. Therefore, we've solved the exponential trigonometric equation by carefully analyzing the different possible cases and finding that the solution set consists of all values of x equal to k pi plus pi over 4, where k is any integer. In this video, we'll solve an exponential equation with two variables. Let's work through this example. 3/2 to the power of x minus y minus 2/3 to the power of x minus y equals 65/36. Let's start by recognizing something important about the two terms on the left side. The bases 3/2 and 2/3 are actually reciprocals of each other. So we can rewrite the second term as 3/2 to the power of negative x minus y. To simplify our work, let's substitute the expression 3/2 to the power of x minus y with a variable t. So our equation becomes t minus 1 over t equals 65/36. Now, let's multiply both sides by t to eliminate the fraction. We get t squared minus 1 equals 65t over 36. Now we'll rearrange all terms to one side to get a standard form quadratic equation. We get 36t squared minus 65t minus 36 equals 0. We need to factor this quadratic expression. After working through the factorization, we get the expression t minus 9/4 times t plus 4/9 equals 0, where t is greater than 0 since it represents a power. Now we can solve for t. Since t is greater than 0 and the product equals 0, either the first factor or the second factor must be 0. From the first factor, we get t equals 9/4. From the second factor, we would get t equals negative 4/9, but since t must be positive, we reject this solution. Now let's substitute back the value of t into our original substitution. We get 3/2 to the power of x minus y equals 9/4. Next, we observe that 9/4 is equal to 3/2 squared. This means that 3/2 to the power of x minus y equals 3/2 to the power of 2. Since the bases are the same, the exponents must be equal. Therefore, x minus y equals 2. But we're not done yet because we have two variables and only one equation. We need another constraint to find specific values for x and y. The problem statement gives us that xy equals 120. Now we can solve this system of equations. If we substitute y equals x minus 2 from the first equation into the second equation, we get x times x minus 2 equals 120, which gives us x squared minus 2x equals 120. Rearranging to standard form, we get x squared minus 2x minus 120 equals 0. We can factor this as x plus 10 times x minus 12 equals 0. So either x equals negative 10 or x equals 12. When x equals negative 10, we get y equals -12. And when x equals 12, we get y equals 10. Therefore, our final answer is x equals 12 and y equals 10, or x equals -10 and y equals -12. Let's verify our answers by substituting them back into the original equation. In this problem, we solved an exponential equation by first recognizing the relationship between the bases, making a substitution to simplify the equation, and then solving the resulting quadratic equation. Since we had two variables, we needed additional constraints, which led us to a system of equations that gave us our final solutions. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.